Let's talk about GraphRAG, which is one of the most significant advances in RAG that addresses fundamental limitations in how we build AI systems that reason over large document collections. Baseline RAG follows a straightforward pattern. You take a user query, convert it into a vector embedding, you then perform a similarity search against your document chunks, you retrieve the top case of most similar chunks, and then you feed those chunks into an LLM context window. And then you generate a response based on that context. This approach works remarkably well when the answer to a question exists within a single continuous text passage. If someone asks about a specific concept and that concept is explained in one paragraph of your documentation, baseline RAG will find that paragraph and generate a good answer. However, there's a fundamental assumption baked into this approach that breaks down in practice. The assumption is that the semantic similarity between a query embedding and the chunk embedding guarantees that the chunk contains the information needed to answer the question. In my experience, this assumption fails in several important scenarios. Number one is that the questions that require synthesizing information across multiple documents simply cannot be answered well because vector search treats each chunk as an independent unit. The retrieval system has no understanding of how information in one chunk connects to information in another chunk. Second is that the multi-hop queries that require following a chain of relationships through multiple entities cannot be answered because the retrieval mechanism has no concept of entity relationships. If you need to first identify one piece of information and then use that to find another piece of information, vector similarity alone cannot perform this traversal. Third is that the holistic questions about corpus level themes or patterns return chunks that happen to contain words like theme or summary rather than actual substantive content from which themes would be derived. Now let's look at these failure modes in more detail to understand exactly where baseline RAG breaks down. Let's talk about two major categories of questions where baseline RAG consistently underperforms, and understanding these categories will help you evaluate whether GraphRAG is necessary for your use case. The first category is multi-hop reasoning. This type of reasoning requires connecting disparate pieces of information through shared attributes to arrive at an answer. Consider a question like who leads the company that acquired Bethesda? To answer this, the system first needs to identify that Microsoft acquired Bethesda and then separate an entity that identifies that Satya Nadella leads Microsoft. These two facts likely exist in completely different documents, and there is no embedding proximity between them, and that would cause vector search to retrieve both. The retrieval system cannot chain these facts together because it has no concept of the relationship between Bethesda, Microsoft, and Satya Nadella. Each chunk is validated independently based on its similarity to the query, and the query itself doesn't contain the intermediate information needed to bridge these facts. The second category is global sense making. These are questions that ask about the entire dataset rather than specific facts. Questions like what are the main themes discussed across this corpus, or how do you differentiate different authors approach this topic, require understanding patterns that emerge across many documents. When you ask baseline RAG about themes, it retrieves chunks that are semantically similar to the word themes rather than the actual substantive content from which themes would be derived. The system has no mechanism to aggregate information across the corpus and identify patterns. What's particularly important to understand is that these failure modes become more severe as the document collection grows. In a small corpus, relevant information might happen to be close together, but as you scale to millions of documents, the probability of relevant information being scattered across non-adjacent chunks increases proportionally. So now that we understand the problem, let's look at how GraphRAG addresses these limitations. Let's talk about what GraphRAG actually is and how its architecture fundamentally differs from baseline RAG approaches. GraphRAG is a graph-based retrieval augmentation generation system developed by Microsoft Research. The key insight is that instead of treating documents as collections of independent text chunks, GraphRAG transforms unstructured documents into a structured knowledge graphs before retrieval. The process begins with entity extraction. Large language models read through your documents and identify entities such as people, organizations, location, events, and concepts. But GraphRAG doesn't stop at just identifying entities. It also extracts relationships connecting these entities along with natural language descriptions of those relationships. These extracted entities and relationships form a knowledge graph where nodes represent the entities and edges represent relationships. Unlike traditional knowledge graphs that use past triples like Microsoft acquired Bethesda, GraphRAG attaches rich natural language descriptions to both nodes and edges. This design choice is intentional because these descriptions are optimized for LLM comprehension and downstream summarization tasks. The next critical step is community direction. GraphRAG uses Leiden algorithm to partition the knowledge graph into hierarchical communities of closely related entities. Think of communities as clusters of entities that are more densely connected to each other than to entities outside the cluster. For each community at each level of hierarchy, GraphRAG pre-generates natural language summaries. These community summaries capture the key themes, important entities, and significant relationship between each cluster. At query time, GraphRAG offers two distinct search modes. Local search traverses the graph to answer entity-specific questions by following relationship paths. Global search uses community summaries in MapReduce pattern to answer corpus-level questions without needing to scan all source documents. Now let's look at how these components fit together in the overall architecture. Now let's talk about high-level architecture of GraphRAG and how the different components work together as a system. The architecture consists of two primary components. The first is the indexing engine and the second is the query engine. Understanding the separation between these two is important because indexing is a one-time operation that you perform when you ingest the documents, while querying happens every time a user asks a question. The indexing engine processes the source documents through a multi-stage pipeline. It extracts the entities and relationships from the text, constructs the knowledge graph from those extractions, detects community structure within the graph using the Leiden algorithm, and generates natural language reports for each community. The output of the indexing pipeline is a set of knowledge structures. The knowledge graph stores entities as nodes with their names, types, and descriptions. Relationships are stored as edges with descriptions and weights that indicate how frequently and consistently a connection appears across your corpus. The community structure organizes entities into hierarchical clusters. Level 0 contains the broadest thematic groupings corresponding to major topics in your dataset. Deeper levels reveals increasingly specific subcommunities within each parent community. This hierarchical organization is what enables GraphRAG to answer questions at different levels of abstraction. The query engine accepts your user questions and routes them to appropriate search mode. For questions targeting specific entities, local search is typically more appropriate. For questions requiring holistic understanding of the corpus, global search leverages the pre-computed community summaries. What makes this architecture powerful is the combination of structured knowledge representation with pre-computed summaries. This enables query types that are fundamentally impossible with vector-only retrieval systems. Now let's talk about the indexing pipeline in more detail to understand exactly how documents are transformed into these knowledge structures. Now let's talk about the complete indexing pipeline and understand each phase of how GraphRAG transforms raw documents into queryable knowledge structures. The pipeline consists of 6 distinct phases, and understanding each phase will help you tune the system for your specific use case. Phase 1 is document segmentation. Source documents are split into text units, which serve as the ultimate units for extraction. These text units also provide fine-grained source attribution, allowing GraphRAG to link answers back to specific passages in your original documents. The size of these text units is critical configuration parameter that we'll discuss in more detail shortly. Phase 2 is entity and relationship extraction. LLM prompts are used to extract all entities from each text unit along with their names, types, and descriptions. The same prompts extract relationship between entity pairs, including the descriptions of how entities are connected and strength scores indicating the significance of each relationship. Phase 3 is summarization. The same entity often appears across multiple text units with slightly different descriptions. This phase consolidates all instances of each entity into a single unified description that captures all discovered attributes. The same consolidation happens for relationships. Now, phase 4 is graph construction. The knowledge graph is built from summarized entities as nodes and summarized relationships as edges. Importantly, this phase maintains links back to the source text units for prevents tracking. Phase 5 is community detection. The Leiden algorithm is applied to detect hierarchical community structure within the graph. This partitions the graph into clusters at multiple levels of granularity. Phase 6 is report generation. Natural language reports are generated for each community, capturing the key entities, relationships, and themes within that cluster. These reports are what enable efficient global search at query time. Now let's look at more closely at the first phase, which is the text unit segmentation, because it has significant implication for both extraction quality and indexing cost. Now let's talk about text unit segmentation and why the chunking strategy you choose here has significant implications for your GraphRAG system. Text units are the fundamental building blocks of the indexing pipeline. They serve a dual purpose. First, text units are the input to entity extraction. The LLM processes each text unit independently to identify entities and relationships. Second, text units provide source references for your answer preference. When GraphRAG generates an answer, it can cite the specific text units that contributed to that answer. The chunk size configuration involves a fundamental trade-off that you should understand. Smaller chunk sizes, typically around 300 tokens, enable more detailed entity extraction. When the LLM processes smaller pieces of text, there is less context to distract it and it can focus on extracting fine grained details. However, smaller chunks significantly increase the total number of LLM calls required for during indexing, which directly increases your costs. Larger chunk sizes around 1200 tokens, which is a default, preserve more context for understanding entity relationships. When entities are mentioned together in a larger chunk, the LLM can better understand how they relate to each other. However, larger chunks may overwhelm the extraction prompt and cause LLM to miss fine-grained details. The chunk overlap is an important consideration. Entities and relationships are often mentioned near chunk boundaries. Without overlap, information at these boundaries might be lost because the relevant context is split across two chunks. Overlap ensures that the entities and relationships spanning boundaries are captured by at least one text unit. In my experience, the choice of chunk size directly impacts both extraction quality and indexing cost. This makes it one of the most important configuration parameters to tune for each specific use case and domain. I recommend starting with the default settings and then experimenting with smaller chunks if you find that important entries are being missed. Now let's look at how entity and relationship extraction actually works. Let's talk about how GraphRAG uses large language models to extract entities and relationships from your documents. For each text unit, the LLM receives a carefully structured prompt with specific instructions. The prompt asks the LLM to identify all entities present in the text and extract these three pieces of information for each entity. First, the canonical name of the entity. Second, the semantic type such as person, organization, location, event, or concept. Third, a comprehensive description of the entity's attributes and activities as mentioned in that text. The entities types can be customized for specific domains. For a general news corpus, types like person, organization, and location work well. But a chemistry, for example, dataset, you might want to add types like molecule, reaction, and pathway. For a legal documents corpus, you might want to add statute like case and legal principle type of concepts. Domain customization significantly improves extraction quality, and we'll discuss this in more in the next section. After extracting entities, the LLM identifies all pairs of entities that have a clear relationship. For each relationship, the extraction captures the source entity, the target entity, a natural language description of how they are related, and a numerical strength score indicating the significance of that relationship. The extraction prompts include several mechanisms to improve completeness. Few short examples demonstrate the desired output format so that the LLM understands exactly what's expected. A gleaning mechanism encourages the LLM to make additional extraction passes to catch entities or relationships it might have missed on the first pass. Relationship strength scores serve an important purpose at query time. When the context window is limited, the system can prioritize stronger, more significant connections over weaker ones. This ensures that the most important relationships are included in the LLM context. Now let's discuss how to tune these extraction prompts for specific domains. Now let's talk about domain-specific prompt tuning and why this step is critical for getting good results from GraphRAG in specialized cases. The default extraction prompts that ship with GraphRAG are designed for general news articles, specify entities like person, organization, and geography. While these work well for news content, they will miss domain-specific entities that are important in your specialized use case. If you're indexing scientific literature, the default prompts won't look for molecules, genes, or experimental procedures. If you're indexing legal documents, they won't look for statutes, case citations, or legal principles. This means important entities in your domain simply won't be able to be extracted, resulting in an incomplete knowledge graph. GraphRAG provides an auto-tuning capability to address this. The auto-tuning process analyzes the sample content from your target domain and generates a specialized persona for the LLM to assume when extracting entities. Based on this analysis, it produces domain-appropriate entity types and few short examples that drawn from your similar actual use case. For example, when auto-tuning on a chemistry dataset, the system might generate entity types like molecule, reaction, or compound. The few short examples would demonstrate extracting these specific entity types for chemistry-related text. In my experience, prompt tuning typically reduces significantly more entities and relationships than actual default prompts. This creates a richer knowledge graph that provides more comprehensive coverage for downstream queries. If your extraction is missing important entities, your graph won't have the structure needed to answer questions about those entities. For enterprise deployments, I strongly recommend investing time in prompt tuning. The domain specificity of your extraction prompts directly determines the utility of your GraphRAG system for your specific use case. Now let's look at how extracted entities and relationships are summarized before graph construction. Let's talk about entity and relationship summarization and why this phase is essential for building a clean, useful knowledge graph. A common pattern in document collections is the same entity appears across multiple text units with different descriptions. Each mention might capture different attributes, activities, or perspectives depending on the context. For example, a person might be described as CEO of company X in one text unit and the author of three best-selling books in another. Entity summarization collects all the instance descriptions for each unique entity and uses the LLM to generate a single comprehensive description that integrates all the discovered information. This consolidated description captures the full picture of that entity as it appears across your entire corpus. Relationship summarization works similarly as well. All instance descriptions for each unique entity pair are collected and consolidated into a unified relationship description that captures the full nature of the connection. This summarization phase serves multiple important functions. First, it reduces graph noise by eliminating the redundant information. Without summarization, you might have dozens of slightly different descriptions of the same. Second, it enriches the descriptions by combining partial information from different sources. Information that's spread across multiple mentions is now unified in one single place. Third, it normalizes now naming conventions to some degree as well. However, there's an important caveat here. Complex datasets with many ambiguous entity references can pose challenges. Different people might share the same name, or the same entity might appear with significant naming variations. In these cases, simple name-based matching is not sufficient, and you might need more sophisticated entity resolution techniques. In my experience, the summarization phase works well for most datasets, but you should validate that important entities are being correctly consolidated rather than incorrectly merged or left fragmented. Now let's look at how the knowledge graph is actually constructed from these summarized elements. Now let's talk about the structure of the knowledge graph that GraphRAG builds and how it differs from traditional knowledge graphs. The knowledge graph is constructed as a homogeneous, undirected, weighted graph. Entity nodes are connected by relationship edges and each has a weight. This differs from traditional knowledge graphs that typically use directed, typed edges with sparse triples like subject, predicate, object. Each node in the graph contains several pieces of information. The entity names identifies a node. The entity type provides semantic categorization. The summarized description captures what we know about the entity from across the corpus and reference all to the source text units where the entity was mentioned, enable the provenance tracking back to the original documents. Each edge contains a relationship description which explains how two entities are connected in natural language. It also contains a weight representing the normalized count of detected relationships instances. This weight indicates how frequently and consistently the connection appears across your corpus. Relationships that are mentioned many times in many documents will have higher weights than relationships that have been mentioned only once. A key design choice in GraphRAG is the use of rich natural language description rather than concise triples. Traditional knowledge graphs rely on structural tuples like Einstein-developed relativity for logical reasoning. GraphRAG instead uses full descriptive text like Albert Einstein developed the theory of general relativity, which revolutionized our understanding of gravity and space-time. This design is intentional because GraphRAG is optimized for LLM comprehension and summarization rather than logical reasoning over structural tuples. The rich descriptions give the LLM more context to work with when generating answers. The graph structure enables a traversal-based retrieval that can follow relationship paths across multiple hops. This is what allows GraphRAG to discover indirect connections between entities that would be invisible to vector search. Now let's examine how community detection partitions this graph into useful clusters. Detection and why GraphRAG uses the Leiden algorithm to partition the knowledge graph. Community detection is a graph analysis technique that partitions nodes into groups called communities. The defining characteristics of a community is that the nodes within the community have stronger connections to each other than the nodes which are outside the community. In the context of GraphRAG, communities represent clusters of entities that are closely related to each other. GraphRAG specifically uses the Leiden algorithm for several reasons. First, Leiden is a highly efficient algorithm and can process large-scale graphs quickly. Second, it produces hierarchical community structure, meaning you can get communities at multiple levels of granularity. Third, it guarantees that all resulting communities are well connected internally, which is important for generating coherent community summaries. The hierarchical structure is a critical feature. Level 0 communities represent the highest level thematic groupings in your database. These correspond to major topics or domains that emerge from the natural clustering of related entities. If you're indexing news articles, level 0 communities might correspond to broad categories like politics, sports, and technology. Level 1 and deeper levels reveal increasingly fine-grained subcommunities within each parent community. Within the technology level 0 community, you might have level 1 subcommunities like artificial intelligence, cybersecurity, and consumer electronics. Within the artificial intelligence subcommunity, you might have further subdivisions. The hierarchical organization is what enables GraphRAG to answer questions at different levels of abstraction. When you need a broad overview, you can query at higher levels. When you need specific details, you can query at lower levels. In my experience, the automatic community detection usually produces sensible groupings, but the quality depends heavily on the quality of your underlying entity and relationship extraction. If important relationships are missing from your graph, the community structure won't accurately reflect the thematic structure of your data. Now let's look at how community reports are generated from these detected communities.